Welcome to our guide on single equation forecasting. This presentation will bridge the gap between econometric theory and practical application using the EViews software. We will cover the core methodology, key concepts, and provide a step-by-step walkthrough of how to generate and evaluate forecasts. As Niels Bohr's quote reminds us, prediction is inherently challenging, especially when looking into the future. This guide is designed to help students and researchers navigate these complexities, offering a practical approach to single equation forecasting. To begin, let's understand why forecasting is not just an academic exercise, but a crucial tool for economic decision-making. Economic agents, from central banks to corporations and investors, are constantly making decisions today that hinge on their expectations of tomorrow. This slide underscores the fundamental economic imperative for forecasting. We have a wealth of observed historical data and can account for known shocks up to a certain point in time. The critical challenge lies in bridging the gap between this known past and the uncertain future. Forecasting isn't merely about drawing a line into the unknown. It's a systematic process of projecting established structural relationships derived from our historical data onto anticipated future conditions. The ultimate goal is to minimize the inherent uncertainty in decision-making, whether that's for setting policy, making investment choices, or developing budgets. It allows us to move from historical analysis to informed strategic planning for what lies ahead. Our forecasting journey begins by identifying the type of data we're working with. For our purposes, we're focusing on time series data. The next critical step is to determine if we need a univariate model, which uses only the past values of a single variable, or a multivariate approach, incorporating other related variables. If we opt for a multivariate approach, we then consider the relationship between these variables. Specifically, we ask if there are any feedback loops present. If such loops exist, where variables mutually influence each other, a more complex VAR or system approach is generally required. However, our current focus is on structural single equation forecasting. This method is ideal when we have a clear dependent variable, y, that is driven by exogenous explanatory variables, x, without those complex mutual feedback mechanisms. Think of it as predicting sales, y, based on advertising spend, x, where sales don't significantly impact the advertising budget. This framework allows for common EViews contexts like exponential smoothing, VAR systems, and importantly, regression models. Dynamic forecasting is what we use for true multi-step ahead predictions into the unknown future. When the model needs a lagged value of the dependent variable, it uses the previously forecasted value. This means errors can accumulate over the forecast horizon. Static forecasting, on the other hand, produces a series of one-step-ahead forecasts. When it needs a lagged value, it always uses the actual observed data from the previous period. It corrects itself at every step. This makes it unsuitable for forecasting the unknown future, but perfect for in-sample model validation to see how well the model fits the historical data. Imagine forecasting tomorrow's stock price using today's price. A dynamic forecast for 2 days ahead would use the forecasted price for tomorrow to predict the next day. A static forecast would use the actual price for tomorrow, once it's known, to predict the next day. After we've generated a forecast, how do we know if it's any good? We need objective metrics to evaluate its performance. After generating a forecast, it's crucial to objectively evaluate its performance. Here, we outline the key metrics used to assess forecast accuracy. The root mean squared error, or RMSE, is a standard metric that heavily penalizes larger errors by squaring them. The mean absolute error, MAE, provides the average magnitude of the forecast error, being less sensitive to extreme outliers than RMSE. For comparing forecasts across different series with varying scales, the mean absolute percentage error, MAPE, is particularly useful as it expresses the error as a percentage. Lastly, the Thiel inequality coefficient, ranging from 0 to 1, measures a model's ability to track turning points, with a value of 0 indicating a perfect fit. Crucially, for all these metrics, a lower value signifies a more accurate and preferred forecast when comparing different models, such as Model A versus Model B. The core of our forecast is this simple equation. The point forecast, y hat t plus h, is our prediction for h periods into the future. It's constructed using the parameters a and b, which are estimated from our historical data sample, from time 1 to t. Crucially, to forecast y, we must have values for our explanatory variables, x, for the future period t plus h. This is the x-factor constraint. These future values must be known, assumed in a scenario, or forecasted separately. The total forecast error comes from two sources: uncertainty about our estimated coefficients and future random shocks, or innovation uncertainty. To forecast sales, y hat, for next month, we need our estimated model, A and B, and a value for next month's advertising budget, X. If we don't know the budget, we can't make the forecast. This mathematical relationship, however, only works if certain critical conditions are met. Let's discuss these assumptions next.
First is structural stability. This is the most important assumption. It means the relationship between our explanatory variables and the dependent variable, captured by our estimated coefficient beta, must remain the same in the future as it was in the past. Second, there should be no major regime shifts. Events like a new tax law, a financial crisis, or a pandemic can fundamentally change economic relationships, making the old model invalid. A model of gasoline demand estimated before 2020, for instance, would likely fail to forecast demand during pandemic lockdowns due to a dramatic regime shift. Finally, as we just discussed, we need data availability. We must have values for all our right-hand side variables for the entire forecast period. Critically, if the underlying structure changes, the forecast will fail. Therefore, it's essential to perform stability tests, such as the Chow breakpoint test available in EViews, before attempting to forecast.
A fundamental assumption in regression is that error terms are random. However, when errors exhibit an autoregressive moving average, or ARMA structure, meaning the error at time t is correlated with previous errors, this predictability can be leveraged to enhance forecast accuracy. For example, if ut equals rho ut minus 1 plus epsilon t, the error is not purely random. EViews automates the handling of these ARMA errors to improve your forecasts. In a static method, where we perform one-step-ahead forecasts within the sample, EViews directly uses the actual observed lagged residual to make the current prediction more precise. For dynamic forecasts, which project into the unknown future, actual residuals aren't available. Here, EViews forecasts the residuals recursively, using the estimated AR coefficient, so ut equals rho ut minus 1. A clever aspect is backcasting, where EViews generates pre-sample values for innovations if initial lagged residuals are missing. This entire process is an automatic feature in EViews, ensuring your forecasts benefit from autocorrection without manual calculation, particularly improving short-term accuracy. The forecasting process in EViews always follows a crucial two-step workflow. First, you must estimate your model, and only then can you proceed to forecast. This is a post-estimation procedure, meaning you cannot access any of the forecasting tools until you have a valid estimated equation object. Once your equation has been successfully estimated and its output window is open, you have two primary ways to initiate the forecast. You can either click the dedicated forecast button directly on the toolbar, which is highlighted here, or you can navigate through the proc menu and then select Forecast. This ensures that the system has all the necessary information, like estimated coefficients, to generate a projection. Clicking this button or menu option will then open the main forecast dialog box, where we'll configure all the details of our prediction. Once you click the Forecast button, this dialog box appears, allowing you to configure all the details of your prediction. First, it's crucial to define a name for your forecast series. Always append a suffix like _f or _dyn to prevent accidentally overwriting your original historical data. You should also save the standard error series, which is essential for constructing confidence intervals around your forecast. Next, you'll choose the forecast method. Select Dynamic Forecast for true out-of-sample predictions into the unknown future, or Static Forecast for in-sample validation. Finally, you specify the forecast sample period, for instance from 2000 Q1 to 2004 Q4. Remember to check the boxes for forecast graph and forecast evaluation to get immediate visual and statistical output, which will be vital for assessing your model's performance. Once we've configured our forecast parameters, we need to understand the output and visualization options available. When selecting Dynamic Forecast as our method, the software will generate a plot comparing our forecast against the actual values, crucially including the plus or minus 2 standard error bands. This visual representation is vital for what we call the eye test. Always prioritize selecting Forecast Graph, because a visual inspection of the trend and confidence bands offers a faster, more intuitive understanding of our forecast performance than merely sifting through raw statistics. Complementing this, selecting Forecast Evaluation generates a table of key accuracy metrics such as RMSE, MAE, and the Thiel statistics, which we discussed earlier. Finally, checking the option to Insert Actuals for out-of-sample observations is important as it merges your historical data with the forecast, providing a continuous plot that greatly enhances the visual assessment of your model's predictive power. In our first step of this case study, we aim to predict the money supply, M1, by utilizing key macroeconomic indicators, gross domestic product, or GDP, and interest rates, denoted as RS. Our approach involves using the natural logarithm of both M1 and GDP to model their relationship. The initial task is to establish this historical relationship. As you can see from the EViews command and output, we run a least squares regression using data from the first quarter of 1952 through the fourth quarter of 1992, encompassing 164 observations. Critically, before we even consider forecasting, we must ensure our estimated coefficients are statistically significant. The output confirms this, with probability values for all variables, including the constant, log of GDP, and RS, being well below the 0.05 threshold. Our R-squared value of 0.98 also indicates a strong fit. This estimated equation forms the stable structural foundation we'll project into the future. We are now moving into the second crucial step of our case study, executing the forecast for validation. As highlighted, the primary objective here is to validate our previously estimated model. To do this, we perform what's known as an ex-post forecast. This means we are forecasting into a period for which we actually have known historical data. In this specific example, we've set our forecast sample from the first quarter of 1993 through the fourth quarter of 1996. In the EViews forecast dialog box, you can see we've specified our forecast series as M1_F and its standard errors as M1_SE. We've also selected Dynamic Forecast, which is crucial for testing the model's ability to generate multi-step ahead predictions. By comparing our model's dynamic predictions with these actual historical observations, we can objectively assess its accuracy and reliability. This critical step verifies if our model faithfully tracks reality, giving us the confidence to then deploy it for making predictions about the truly unknown future. Our goal here is to validate the model. We generated a dynamic forecast for a period after our estimation sample, but for which we have known data. The first and most intuitive check is the eye test, comparing the blue forecast line against the red actual data. We observe that our forecast successfully captures the general trend and turning points of the actual series. Crucially, we also examine the confidence bands, represented by the shaded area. These plus or minus 2 standard error bands represent a 95% confidence interval. The fact that the actual data remains almost entirely within these bands gives us strong confidence in the model's statistical robustness. This visual assessment provides an encouraging start, suggesting our model performs well. However, while the visual check is encouraging, we need to back it up with hard numbers. Let's look at the statistical evaluation of this forecast next. Now we perform the statistical audit. The root mean squared error and Thiel coefficient are both very small, which is a good sign for our forecast accuracy. The most insightful part is the decomposition of the Thiel inequality coefficient. The bias proportion tells us if our forecast is systematically too high or too low. A value close to 0, like the 0.0001 we see here, is excellent, indicating no systematic over or under prediction. Furthermore, the covariance proportion measures the unsystematic error, or random noise. We want this to be as close to 1 as possible. Our value of 0.9789 is very high, indicating that most of the forecast error is purely random, not due to a fundamental flaw in our model specification.
While EViews' graphical interface is excellent for learning, mastering its command line syntax offers significant advantages, especially for repetitive tasks. This cheat sheet summarizes the essential commands for forecasting. For a default dynamic forecast from an equation object, like EQ01, you simply type EQ01.forecast y hat. If you need a static forecast, perhaps for in-sample validation, you'd use the .fit command, EQ01.fit y hat static. To be more explicit with a dynamic forecast and also save the standard errors, which are crucial for constructing confidence intervals, use EQ01.forecast(d) y hat yse. You can also efficiently set your forecast sample period directly from the command line using the SMPL command before running your forecast. For example, SMPL 2000 Q1 2005 Q4. The real power of these commands lies in automation. You can save a sequence of these commands in a program.prg file, allowing you to run complex forecasting routines with a single click, saving immense time and ensuring reproducibility. We've covered a lot of ground, from the basic principles to practical implementation. Let's now summarize the key takeaways from our discussion.
Thank you for joining this presentation on single equation forecasting. As a final thought, always remember that the most effective forecasting model is one that minimizes the error of the future, not merely one that fits historical